All right, so this is Module 13, Thermodynamics. We've looked at some stuff already with the substances of equations. Now we're going to look at the energy behind the reaction. And the first thing we need to learn is enthalpy. Now, what is enthalpy? This is the heat energy that's being absorbed or released within the chemical reaction. And it can be seen as endothermic or exothermic. And what this means is if something is endothermic, as you see down on the bottom here, it absorbs energy from the system. If it's exothermic, it releases energy to the system. And the system is just its surrounding. Okay. This figure right here shows us an energy diagram. Here's our equation right here. This is how much potential energy is stored in these molecules. And we need some kind of activation energy in order to get this reaction to get started. But once it reaches this point and actually starts, it's spontaneous from that point and will continue on creating these elements or molecules until it comes to completion or the equation is balanced. Now, in this particular graph, you'll notice that this is way up here at 100. Sorry, my screen is not cooperating. When it ends, it's way down here, closer to maybe about 50. We'll say it's about 50. Okay? When you start with high energy, this is potential energy, and the graph ends at a lower potential energy, which means it's releasing all of this energy into its environment. This would be an exothermic reaction. If it were an endothermic reaction, we'd be starting somewhere down here, maybe have some activation energy to get it started, but then it would end at a much higher. So when you go from a low energy level and you end at a higher energy level, that would be endothermic, meaning that it needs to get energy from the environment in order for it to complete the reaction. Okay. You remember the first law of thermodynamics? Energy is neither created nor destroyed in a reaction. We need to remember that as we go through this. So, as the energy goes from potential energy to this kinetic energy, or from kinetic energy back into potential, depending on the type of reaction, this energy is stored in the bonds of the molecules. So if we have this reaction, whoop, that's an error right there. That should be a lowercase l. If we have this reaction, hydrochloric acid plus sodium hydroxide creates water and sodium chloride plus energy. This would be an exothermic reaction. Now, how we know this is because energy is over here on the product sides. Okay? When energy is on the product side, then it is an exothermic reaction. All right? Now, here's another equation, but you'll notice that energy is over here on the reactant side. This screen is going to drive me crazy until I figure out how to really use it. Sorry. So when you have energy on the reactant side, that means that it's endothermic. Okay? We'll have to remember that for later on. All right. So this is the symbol for enthalpy right here, delta H. Okay, it's the change in enthalpy, or scientists usually just call it enthalpy. And this is the energy change that goes along with this chemical reaction, any chemical reaction. The units for this, it can be in joules, kilojoules, calories, kilocalories, kilojoules per mole, joules per mole, all of these. The most common one that we'll use are right here, the kilojoules and the kilojoules per mole. We'll use those most of the time. You'll see calories and stuff, but these are the two big ones that we'll be using. Now, can this enthalpy, delta H, be positive or negative? Well, it can. And when we deal with these equations, we'll get to in a minute, if you have a positive value for enthalpy, for the change in energy, being positive is an indicator that it is endothermic. It needs energy from the environment in order for it to take place and complete the reaction. If the enthalpy, the change in energy, is negative in value, then it is exothermic, meaning that it's releasing energy to the environment. So this one we would find on the reactant side, and this one, exothermic, would be on the product side. So here's our equation. It's a complete combustion of methane. Okay. Whenever you have complete combustion, remember it requires oxygen, and your final products are always carbon dioxide and water. And in this case, we're going to be adding the energy involved with it. And since this is an exothermic reaction, as these two combine and create these, it's going to release this energy to the environment. All right, so how do we measure enthalpy, or this change in energy level in reactions? Here are a couple of ways. Calorimetry, we've already done the math behind this in class. We'll take a look at this as I get a little bit better with my camera equipment in this new software I got. I'll do some of these labs on video and set them up so you can see them. Okay. Using bond energies is another way, using Hess's law, which we'll talk about shortly, as well as using Gibbs free energy, which is denoted as delta G. So, like I said, calorimetry is the experimental way of doing it. This is a calorimeter. This is like the one that we would use in class if we were actually in class together. There's a container inside here that you can put water in. You can put other substances in there with it, and it holds all of the heat energy inside. That heat energy, one of these holes would have a thermometer in it, and we can keep track of that. And that would let us know whether something is absorbing energy or releasing it based on the temperature, and we can use those numbers to figure out what the enthalpy is, the change in energy. This is a little easier way of doing it, bond energies. Now, this bond energy, we have to use this chart in order to do this, and this is in your book. It's 13.2. It's not too bad. It does force us to go back and reacquaint ourselves with the Lewis dot structure in order to do this. So you have an equation, you have to be able to write it out in Lewis dot structure, and then for every bond in the molecules, we can come on here and see what the bond energy is. And how do we know this? Well, okay, you have a carbon-hydrogen bond. That carbon-hydrogen bond with a single bond is going to have the same amount of energy in it. It's like a car with a 25-gallon gas tank. You can't put 50 gallons in it. It's 25 gallons. It's going to be the same. Same with these types of bonds. Double bonds, triple bonds, they have a certain amount of energy in them with these elements. And it's pretty much the same. It's been tested over and over. So we have this chart, and these are common ones that we would use. It's usually measured in kilojoules. You'll see on the chart, it mentions kilojoules per mole. This is how much energy per mole that it would require or release. So the formula for finding enthalpy while using bond energy is as follows. We've got enthalpy, delta H, is equal to the energy required to break bonds minus the energy released when bonds are formed. So what does this mean? Energy required to break a bond. If you look at an equation, okay, we have our little arrows here. We have our reactants on the left, and we have our products. It's a lot harder to write on this screen than you would think. There's definitely a learning curve. Sorry, that's terrible writing. We have our products on the right. So the energy required to break a bond, that has to do with the reactant side. And energy released when bonds are formed go on the product side. So when we take a look at our problem on the next slide, our reactants will be over here, and we'll subtract the energies we get from the products. All right, so here's our equation. N2 plus 3H2 creates this over here, and we know it's going to create some kind of energy. I kind of have it over here already, showing that it's going to be exothermic. This endothermic energy would be over here. So remember Lewis dot. Here's nitrogen, okay? N2, written out in Lewis dot structure. We have an N, triple bond between the N's, okay? We have 3 hydrogen. Remember, hydrogen is bonded to another one, a homonuclear diatom. So we have 3 of those. There's 1, there's 2, there's 3, okay? NH3, we have 2 of these, okay? Now, what you notice here is that there is 1 NH bond, another NH bond, and a third NH bond. So each one of these molecules has 3 NH bonds, and we have 2 molecules. So that gives us a total of 6 NH bonds. Okay, we have 3 of the HH bonds and 1 nitrogen triple bond to a nitrogen. So when we look at our table down here, start with our nitrogen over here. We find nitrogen, triple bond nitrogen. There it is. That has a bond energy of 942. We look at our hydrogen, hydrogen. We have 3 of them. Here's hydrogen, hydrogen bond. Each one is 432. We have 3 of them. So that would be 3 times 432. And our nitrogen, hydrogen, with these 2 molecules, we said we had a total of 6. So we find nitrogen, hydrogen, which is right here. That's 386. So we have 6 of them. So it'd be 6 times 386. Okay. We can multiply those out, but I have it on the next slide, which we will take a look at here. All right, so here we go again. This is what I just showed you. We went through the values. So for nitrogen, we said it was 942. Hydrogen, there were 3 of them at 432. Those are the reactants. And then the products, we have 6 of the NH bonds. So subtracting 6 times 386. We do the math here. You'll see that the reactants have 2238 kilojoules per mole. The products have 2316 kilojoules per mole. Subtract, we get a negative, or one of these days I'll get this to work correctly. We have a negative 78 kilojoules per mole, okay? Now, we put that, since we know it's negative right here, that means it's exothermic. When delta H is negative, it's exothermic, and it goes on the product side over here. Now, wait a minute. Where's the negative sign, you're asking, right? Well, that just tells us it's being released into the environment. The heat is being released. So it doesn't go down here as negative. It says it's a product. We have heat energy, and it's going into the environment. So it's positive here, but the negative sign tells us it goes on this side. If this were positive 78, that would say it's an endothermic reaction, and it would go over here, and it would just be a plus 78 kilojoules per mole over here. Okay, so the negative sign doesn't follow it into the equation. That just tells us whether it goes on the reactant side or the product side. Negative, exothermic, goes on the product side. Positive, endothermic, goes on the reactant side. Okay. So here's another one, methyl alcohol. Here's our equation. Again, we have to be able to write this down in our Lewis dot. So we have CH3OH. Remember, C is going to be your center. We have an OH, and we have 3 hydrogens on here. And then we have O2, which is just O, double bond O. And then we have CO2, that's C, double bonded to 2 oxygens, and then H2O, which is just oxygen with a single bond to 2 hydrogens. Now we have 4 of these. We have 2 of these. We have 3 oxygen bonds, and we have 2 of these methyl alcohols. So we're going to have to count up all the bonds. So you notice in here that we've got 1, 2, 3 CH bonds. Okay, but we have 2 of them, 2 of these molecules. So when we have both of those together, that means we have a total of 6 CH bonds. We have a CO bond in both, so that becomes 2 CO bonds. And then we've got an OH bond, 2 of those, 1 for each. It doesn't matter whether you write OH or HO in this chart, it'll give you the same thing. Okay, so those are all the ones for the methyl alcohol. O2, we have 3 of these. These are pretty easy. On this one here, we have 2, so there's a double bonded carbon oxygen there and another one there. We have 2 of them, so that means there's a total of 4 C double bond O. Okay, and I didn't write it here, but we have 3 of these, 3 double bond O's. And hydrogen, or water, we've got a hydrogen-oxygen bond there, hydrogen-oxygen bond there. So that's 2 for each, and we have 4 of them. So that gives us a total of 8 hydrogen-oxygen bonds. Okay, so from here, now we would go to our chart and we'll look up what the bond energy is for a carbon-hydrogen bond, multiply it by 6, with the bond energy for carbon-oxygen, multiply it by 2, energy for oxygen-hydrogen, multiply it by 2. That would give us all the energy for that methyl alcohol. Same thing for the double bonded, multiplied by 3 of the oxygens, and then the carbon-oxygen here multiplied by 4, and the hydrogen-oxygen multiplied by 8. Okay, remember that these over here are the products, and these over here are the reactants. So when we find our enthalpy, which is delta H, it's going to be all of these values minus all of these values. Okay? All right. So when we do this, and we add up all those values using the chart, we'll have 5583 kilojoules per mole for the reactants and 6866 kilojoules per mole for the products. Do the math, negative 1286 kilojoules per mole. So what does this tell us? Look, there's a negative sign right there. Since it's negative, this is an exothermic reaction, and this value would go on the side with the products. Okay, there it is. Again, no negative sign. It just, that negative sign tells us which side it goes on. All right. Okay. Our next one, Hess's law. Enthalpy is what's called a state function. And what the heck is a state function? Well, it's a function where the quantity depends solely on the final destination. It doesn't matter how you get there. Kind of like that old saying, all roads lead to Rome. Or in this picture up here, I've got this mountain. You're trying to climb to the peak way up here. It doesn't matter whether you take route C, route D, E, F, A, or B. You know, some look a little bit easier than others. It doesn't matter. Any one of these routes is going to get you from the bottom of the mountain to the top of the mountain. And what that means is any of these reactions, it doesn't matter how slow, how fast, or what direction the reaction takes, as long as you get to the end product, then the energy required to get there is going to be the same. Okay? If you have a steep slope that you're walking up, okay, you're going to use a lot of energy it may be a shorter distance, but you're going to use a lot of energy because you're climbing up that hill, the potential energy. If you find another path that meanders real slow and goes way out and around and finally gets to that high, well, you're not going to exert as much energy at one moment in time getting there. But when you do finally get there, you'll still burn the same amount of calories as you would if you were going up this steep route. And that's kind of the process they're saying is taking place. All right, so if we know the enthalpy of each substance, since it doesn't matter how we get there, it's going to be the same amount, then we can just find the differences between the enthalpies of the products and the reactants, and that'll give us our change in enthalpy. And we can do this by using the enthalpy of formation, which is another table, 13.3 in your book. And this is the equation that follows that. The enthalpy is equal to the sum. This is a math symbol right here. It means the sum of the enthalpies of the products minus the sum of the enthalpies of the reactants. Okay? This H, or the subscript F and the degree symbol, this Hess's law, it works if you're at standard pressure and temperature. Okay, and that's pretty much what this is telling us, that this only works in that situation. And we, for our purposes, we're going to assume everything is at standard temperature and pressure. Now, one thing we need to realize when we look at the chart, it will make sense more in a minute, is that when we're trying to calculate the values that we're going to find the sum for the products and the reactants, the enthalpy of an element in its elemental form is always zero. Okay, so you won't see it on the chart, but know that if it's in an elemental form, then it's zero. So what does that mean? Well, if you have O2, that's how oxygen is in its elemental form, right? It's always bonded to another one. That would equal zero. Okay? If you have N nitrogen, let's say N2, but it's in a liquid form. Okay, nitrogen is not normally in a liquid form. It's not its natural state. Its natural state is a gas. Okay, so this would not be in its elemental form, which means that is not equal to zero. If N2 is in a gas form, boy, my handwriting is terrible on here, then this would be in its elemental form, and that would be equal to zero. Okay, all right. So, what is the enthalpy of the following reaction? Here's our equation. We have 2NO gas plus oxygen is equal to 2NO2 in a gas form. Okay, so we can use our chart for this, which do I have on the next page? I didn't put it in here. Okay, so in your book, there is a chart for this. Okay, here you go, your enthalpy of formation right here. This is a chart we would use when we're trying to figure out in this equation. Here are the bond energies we just did with the Lewis dot structure. This is the next one. So in this situation, make this a little easier to see here. Okay. You'll see in this reaction we have 2NO. Now, you've got to take into account the phase that it's in. You'll notice here that this is a gas. These are all gases. You have to be aware of that. Otherwise, you could grab the wrong value. So if we have 2NO and it's a gas phase, we come over here to our standard enthalpy of formation. We find NO2, or where's that? NO. There it is in a gas phase. And that tells us the enthalpy of formation right there. We have oxygen, O2. Oh, look, that's how it is. Elementally, that's how it is. So that's equal to zero. Now it forms our product, NO2. Okay, we come back to our chart over here. Look, there's NO2. It's in a gas state, which this is. So the enthalpy of formation is 33.2. Now we have 2 of the NO2, so just like before, 2 times 33.2. We have two NOs over here, so that's 2 times 90.3, which we got from right here. Oxygen is 0. We add these up. We go to our equation. The enthalpy is equal to the sum of the enthalpy of formation for the products minus the sum of the enthalpy of the formation for the reactants. Now, what do you notice that's going on here? They're taking the reactants and they're moving them in the back side of the equation, and the products are over here in the front of the equation. This is different than what we just did in the enthalpy equation where it was reactants minus the products. Okay, you got to pay attention to that. But just like before, you multiply these numbers together, you put them in this equation. In this particular situation, we've got 66, oh, excuse me, we have, my bad, 66.4 kilojoules per mole in the product that comes over here, and 180.6 kilojoules per mole in the reactants that comes over here. We do the math, subtract, that gives us the enthalpy is equal to negative 114.2 kilojoules per mole. And what does that tell us? Well, look, there's our negative sign. So as far as the equation goes, this would go on the product side over here, and that it is exothermic. All right, another example. We've got C2H6O in a liquid state, oxygen in its natural elemental state, CO2 in a gas phase, and water in a gas phase. Again, we would go to our chart. Let me bring this back over here. Okay, so here we have C2H6O, and we go to our enthalpies. Don't get confused with the standard entropies. We'll talk about that later. But C2H6O in a liquid form, we have a negative 278. So there's our negative 278. Oxygen in its elemental form is 0. Carbon dioxide as a gas. Find CO2 on here. As a gas, we have a negative 394. There are 2 of those right there. And water as a gas. We come over here, we find water. There it is as a gas, negative 242. We have 3 moles of that, so 3 times negative 242. Okay. Again, we crisscross here, so our reactants coming over here, and the products over there. So we have 2 times negative 394 plus 3 times negative 242 for the products, subtracting our reactant, which oxygen is 0, so that just leaves us the negative 278. So we do our math here, we get negative 1514 minus a negative 278, which subtracting a negative is the same thing as adding a positive. So that gives us a negative 1236 kilojoules per mole. Again, it's negative. That tells us it's exothermic. It goes on the product side of the reaction over here. It would be plus a, 1236 kilojoules per mole. Okay? All right, let's move this out of the way again. Do this. There we go. All right, entropy. So what is entropy? It's basically the tendency to lean towards chaos in the universe. Everything starts out orderly and organized, but wants to go towards chaos. So here's a good example. Here's your average room. Everything's nice and neat, put away. You give it a couple of days, and it looks like this. Now, can you start having a room like this, and then it just naturally want to go back to being clean? No, you got to put the work in and do it. But it normally goes from ordered to chaos. That's kind of the best way I can think of to explain entropy. With entropy, we need to remember the second law of thermodynamics is that entropy, chaos in the universe, will increase or stay the same. It will never decrease. Now, what the heck does that mean? That if you've got something that's ordered and organized and it gets all messed up, that it'll never get back to being ordered and organized, kind of like the room I just showed you? Well, no, it will, but we need to account for that extra energy as it's being released or absorbed from its surroundings, from the environment near it. And once you take that into account, then yes, it will never decrease, but it may stay the same. Okay, so a measure of disorder that exists in a system. Okay, changes with the phases make a difference in this. This one isn't going to be as difficult as the first two we spoke of, because basically what we're doing here is that we're trying to determine the sign of entropy. Okay, that's all we need to do here. We're not doing math involved with this. It's just, what is the sign of entropy? We'll do math later. So here are our states. Okay, a solid has less chaos than a liquid, which has less chaos than a gas. So you think about it, the solid is organized, structured, held together. Everything's in its place, molecular wise. If, let's say, ice, okay, that ice becomes a liquid, now it's not so structured and organized. All the molecules are flowing all over the place, moving around, so there's a little more chaos there. Now you take that liquid and change the phase into a gas. Now those molecules are really moving around much farther apart, a lot more movement, so there's more chaos. Okay, so as the entropy increases, it's usually because there's a temperature increase. If entropy increases also with a increase in matter or larger size. Okay, so the change in entropy is greater than or equal to 0. That's basically what this is saying up here, that entropy in the universe will increase or stay the same. So entropy is either going to be greater than or equal to 0, and it will never be less than 0. So to determine the sign, well, okay, it'll be less than 0, but that, like I said, because of the energy in the environment, it can account for that. But in the equation, or in our chemistry, to determine the sign of entropy, you basically pick the side of the equation with more entropy, with more chaos. So we remember our phases here. Gas is more chaotic than liquid. Liquid is more chaotic than a solid. So we're just looking at our phases and how many moles of each of these we have to determine which side has the most entropy. And whichever side that is, whether it's the reactant side or the product side, will determine the sign. Okay, let's take a look. So here's our equation. We have a zinc that's solid, hydrochloric acid that's aqueous, it's in a liquid solution. We have zinc chloride on this side that's in a liquid solution, and we have hydrogen gas. So what is this going to be? Well, there's a solid right there. There's liquid, and there's a gas. There's our big giveaway right there. It doesn't matter whether there are 3 moles over here or 5 moles over here. The fact that this has a gas on this side says that this has greater entropy. It's more chaotic just because it has the gas. And because of that, this makes the change in entropy positive. Okay, here's another one. We have nitrogen, this is a gas. We have hydrogen as a gas, and we have ammonia as a gas. Oh, see, now we have all 3 gases. So now we have to look at the number of moles. We have 1 mole of here, of the nitrogen. We have 3 moles of the hydrogen, so that gives us a total of 4 moles on the reactant side. And over here, we only have 2 moles of ammonia. So the reactants have 4 moles of gas, the products only have 2. Therefore, the reactants go from high energy, high entropy, to low entropy over here. 4 to 2. And because you're going downhill towards the products, that means your entropy is negative. Okay, on our previous one, we were going uphill. Lower entropy over here. Whoops, sorry. Lower entropy over here, higher over here. You're going uphill, and that makes it positive. All right, here's another one. We've got solid and a solid, liquid, liquid, and liquid. Okay, so these are solid, these are lower in entropy, right? They're more organized. This is higher over here because they're liquids. No gases, doesn't matter. We're not worried about the gases since it's not here, but since this does have liquid in the product side, no liquids over here. These are all solids. That means that you're going from low entropy, low chaos, to greater chaos. You're going uphill. Because it's uphill, it's positive. All right, so here's our next one. Gibbs free energy, delta G. It's used to determine if a reaction will take place or not, basically whether it's spontaneous or non-spontaneous. And for this to happen, there has to be no change in entropy in the surroundings. As I said before, that it can't change. So we've got to account for this. It also tells us whether or not a reaction is consistent with the second law of thermodynamics. If it is, then the reaction is spontaneous. If it is not consistent with the second law, then it's not spontaneous. But as long as our Gibbs free energy, delta G, is negative, the reaction is spontaneous. So basically, delta G is always going to be less than 0 for spontaneous reaction. And here's the equation for Gibbs. It's Gibbs free energy, delta G, is equal to enthalpy, we've already talked about this one, delta H, minus temperature times entropy, delta S. Okay, temperature is going to be in Kelvin. Our units in here are going to be kilojoules. This will be kilojoules per Kelvin, but you got to make sure you pay attention to your units of energy. So here's the equation. Let's take a look. Will delta G, will Gibbs free energy be negative? When will it be negative? Well, if enthalpy is negative and entropy is positive, it would give you something negative. Let's put this equation on here so we can take a look at this. Okay, so if delta H is negative and delta S is positive, okay, we'll have a negative number here. We have a negative times, a positive times a negative, okay? That'll give us a negative number over here. This is always going to be a negative number. If delta H is negative and S is negative, let's take a look at this. All right, so now we've got a negative enthalpy. We have a negative entropy times the negative temperature. That's going to give us a positive value on this side. So this could be a positive value over here. Now, this could be spontaneous if you have a negative enthalpy and a positive temperature and entropy over here, but it depends on how big this number is right here. Okay, so if you have 5 plus, let's go with -5. -5 plus 4, well, that still gives you a negative number because this is low enough. But if we have -5 plus 6, now it's become positive. That's not 2, that's 1. Okay? So now you could see that this is kind of iffy. It depends on, it comes down to this right here, the temperature. Is the temperature high enough or low enough to make this stay negative so Gibbs free energy can be negative? Okay, so that's kind of questionable. But this one is always, if enthalpy is negative and entropy is positive, that will always give you a negative Gibbs free energy. All right, can it be positive? Well, for the same reason. If you've got a positive enthalpy, well, then that's going to change your sign for the Gibbs free energy. We can use this table, another table, 13.5 in your book, to determine whether reactions are spontaneous or not. Again, as with all enthalpy, all elements that are in the elemental state will be equal to 0. And this table only works if you're dealing with standard temperature and pressure, which we're going to assume that we are. So here, again, we're using a chart. So you have Gibbs free energy is equal to the sum of the Gibbs free energy of the products minus the sum of the Gibbs free energy of the reactants. So let's take a look at this here. I thought I put the chart in here. I guess I didn't. Okay, so here's an example of Gibbs free energy using the equation here. Okay, we have 2NO gas plus oxygen gives us 2NO2 gas. Now, in this problem, they give us the enthalpy. It says that the enthalpy is negative 114.2 kilojoules. The entropy is negative 147 joules per kilogram. Now, you got to remember, you got to keep your units the same. So if this is joules per, I said kilogram, I mean joules per Kelvin. We need to convert this to kilojoules, which basically is moving the decimal 3 spaces to the left. So that's negative 0.147 kilojoules per Kelvin for entropy. Now, our enthalpy, delta H, is showing negative. Our delta S, the entropy, is also showing negative. So based on what we were talking about earlier, the first assumption is that our Gibbs free energy is going to be positive. Let's see what happens. We also are given our temperature here. It's 532 degrees Celsius, which we need to convert to Kelvin. It comes to 805 Kelvin. So here's our equation. Gibbs free energy is equal to the enthalpy minus the temperature times the entropy. So we just plug in our values. We've got negative 114.2 kilojoules for our enthalpy minus our temperature in Kelvin times our entropy with the converted units into kilojoules right here. Multiply that out, we got negative 118. Don't forget your significant figures. We've got negative 114.2 minus a negative 118. You notice we're subtracting here, which means that we have to be as precise as our least precise, which would be 118. So our answer ultimately will not have anything to the right of the decimal. So we subtract this, we get 3.8. That rounds to 4 kilojoules. This is a positive number, which all of this tells us that this reaction is not spontaneous. What temperature would this reaction be spontaneous? Remember, in order to be spontaneous, Gibbs free energy needs to be less than 0. So if we take the equation and we set it to less than 0 and isolate for the temperature, then we'll be able to figure that out. So we've got enthalpy minus temperature times entropy. All has to be less than 0. So if we subtract delta H from this side, we would subtract over here. That gives us negative T delta S is less than negative delta H. Divide both sides by entropy. Now, we can get rid of this negative sign here. We bring it along. So those would cancel. That cancels. Leaving temperature is less than these cancel. Enthalpy divided by entropy. Okay, and in this case, which we have over here, we plug in the values for enthalpy and entropy. Do our math. Don't forget sig figs. We've got 3 significant figures. We get a temperature of 777 Kelvin. So in order for this reaction to be spontaneous, the temperature has to be less than 777 Kelvin. All right, so that's it for our notes. Feel free to go back and review those. We are going to move on to extra practice problems. Let's get out of that. Open this up. All right, so in your book, extra practice problems. Oops, just turn my board off. All right, this is problem number 1. Which of the following substances will have a change in enthalpy of 0? So what did I tell you in the notes about this? The only time you would have a 0 for substance is if it's in its elemental state. So that obviously is going to eliminate, it's going to eliminate that. Bromine, is that elemental? Well, it's an ionic state. See the negative sign? So it doesn't include that. That's not standard. Chlorine? Chlorine normally by itself? No. So that's not 0. Cl2 as a gas? Yes. That is in its elemental state. N2 as a liquid? No. That's not natural. This is the natural state. So of all of these, the only substances that would have an enthalpy of 0 would be the chlorine gas and the nitrogen gas. Okay? Problem number 2. This a little bigger. Which of the following diagrams indicates an endothermic reaction, and what is the enthalpy of the reaction? Okay, so here are 2 things. I showed you on the chart that if you're starting up high, and you'll always have some kind of a bump in the reaction, but then you finish down low, that means that you've lost energy. That means this energy has gone into the atmosphere. That means it is exothermic. Okay? On this one, we're down here really low. We have all this energy put into the reaction to get up here, and then it finishes and it ends way up here. So you're having to take energy from the surrounding in order to get this reaction to take place, and you end way up here. You put all this energy into it. That means that this is endothermic. It requires energy. So which of the following indicates an endothermic reaction? Well, it's going to be this one. Okay, and then they want to know, what is the enthalpy of the reaction? Well, the enthalpy, the change in temperature, is from way down here to way up here. So if we were to draw this line across somewhere, and then I kind of went down a little low, it's probably closer to there. This is just below 20. It could be like maybe 18. It's really close. Let's say that's about 20. Because we're totally going to have to guess up here. And let's say that that's maybe, it could be 70. It looks a little higher, maybe 75. I'm going to guess that it's maybe 75. Okay, so if we've got 75 minus 20, that gives us a difference of 55. So from here to here, the enthalpy of the reaction is 55. That's the change in energy, okay? That's how you read this chart. If we were to look over here, this is just below 100. It could be, let's see, that's 75, and it could be like 90, 95. And this looks like it's just above 50, maybe it's 55. Okay, so if we've got 95 and we're subtracting 55, that's going to give us 40. So the change in enthalpy in this one would be 40. Okay, all right. So I can do that later. Let's go to our next one, number 3. For the diagram above, which represents the reaction with the highest activation energy? Okay, so activation energy, that's the amount of energy needed to get the reaction to start. Okay, and you'll notice right here, this little bump, that's the activation energy. Okay, right there. Which one has the higher activation energy? Well, obviously this one does, right? So diagram number 2 has the highest activation energy. Number 4. All right, is it possible for a reaction to occur if the reaction results in a decrease in entropy of the chemicals involved in the reaction? Okay, the answer to this is yes, it can. Okay, the heat released must be taken up by the surroundings. Therefore, you have an increase in entropy of the surrounding. This goes back to that question I talked about, that entropy is always tending towards chaos. But you can have a decrease in entropy, but you have to remember that you have to take the surroundings into account, because that's where that energy is going to, or coming from for that matter. Okay. Number 5. All right. What is the sign? Whoops, I forgot to put my little delta in there. What's the sign of the change in entropy for the following reactions? Okay, remember with entropy, we're just looking at the sign, so we have to take all the phases into account. Here we have aqueous, those are both liquid. Okay, they're all liquid. Now we have to see how many moles. There's 1 mole there, there's 2 there, so there's a total of 3 moles on this side, and that's 1 molecule, so there's only 1 mole on that side. You're going from an area of high to an area of low. That is downhill, which means entropy is going to be negative. Okay, going from high chaos to low, it's a negative entropy. Okay, let's look at B. Here we have a gas, and look, they're all gases. So again, we have to take the moles into account. There's 4, there's 5, so there's 9 moles of gas over here. There's 4 and 6, there are 10 moles of gas over here. So we're going from an area of relatively lower entropy to an area of higher entropy. So this is uphill, so that means that you're going to have a positive entropy. In C, we have a solid, a liquid, a solid, and a gas. You don't even need to worry about the solid or the gas or the liquids. Just because this side has a gas on it, this side is going to be more chaotic. So you're going from relatively low state of entropy to a higher state. That's uphill, so your entropy is going to be positive. Okay. D, we've got aqueous, liquid, and a gas. And we have aqueous and aqueous. Again, same thing, but just the opposite. Now in the reactants, we have a gas. Doesn't matter about anything else. The fact that that has a gas means that we're going from an area of high to an area of low entropy. That's downhill, which means our entropy then is negative. Okay, that's all we need to do for that one. Let's move on to our next problem here. All right, what is the enthalpy of the following reaction? And this is asking us to use the bond energies, which means we need our chart. Let me bring this over. Okay. So here's the chart for bond energies on top here. So again, we need to remember our Lewis dot structure. Here we have CO2. So that's, okay. Okay, that's our CO2. Here we have HCl. There are 4 of them. That's HCl. So we have 4 of those. So when we get our number, we'll multiply it by 4. There are 4 HCl bonds. Here there are 2 of the C double bond O's. So we'll find that number and multiply it by 2 of them. Okay. Other side of the equation, we have CCl4. That would be a carbon with 4 chlorines. Okay, that means that we have 4 carbon-chlorine bonds. There's one, there's another, another, and another. So that would be 4 of the CCl bonds. So when we look up our number, we would multiply it by 4. And then we have water. Okay, we have 2 molecules, but in each molecule there are 2 OH bonds. So since there are 2 of them, that gives us a total of 4 of our OH bonds. So when we look up this number, we would multiply it by 4. Okay, so now let's bring up our chart here. So we've got C double bond O. That's right here. That's 179 right there. Excuse me, 779. So 2 times, I can do this, 7, let me get that number again. 799, not 779. 799. And then we've got 4 of our hydrogen chlorine right there. It's 428 for each of them. Okay, so 4 times 428. And our next one, we've got 4 of the carbon-chlorine bonds. There's carbon-chlorine right there, 327. So, 327. And our last one is the hydrogen-oxygen. Come back, there's HO right there. That's 459 for each of those. So, we'll put 459 in there. All right. So that's how we would set it up. We add these together, which, let me see, I think I did those numbers already. All right, so this would come up to 1598 plus 1712. This one here is 1308. And our last one is 1836. All right, so our equation again, remember, enthalpy is equal to the sum of the enthalpy of formation for the reactants minus the sum of the enthalpy of formation for the products. I apologize, my handwriting is terrible on here. Hopefully it'll get better. So reactants. We've got 1598 and 1712. Minus 1308 plus 1836. Okay, that gives us, when we do all this math, it comes out to 166 kilojoules. So our change in enthalpy there is 166 kilojoules. Okay, you notice that it's positive. So what does it tell us about this reaction? Okay, if it were negative, it would be over here on this side, which means that it's a product, but it's positive, which means it's endothermic. And we need to add this energy to this reaction in order for it to create those. And it'll get this from the environment usually. Okay, all right, that's number 6. We're almost done already. Okay, for number 7, it says use Hess's law to determine the enthalpy of formation. In Hess's law, we've got our chart right here. Okay, so we just look up each value. We have NH3 in a gas phase. So we come down here, here's NH3 in a gas. It's a negative 45.9. So over here, we have 4 of those. So that would be, okay, hold on here. 4 times, is that right? 45.9? Yes, negative 45.9. Okay. We have oxygen, okay, in its standard state. That's how it's found. So, whoops, oxygen is going to be 0. And then on the other side of the equation, we've got NO gas. Go back to our chart. Here's NO gas, that's 90.3. We have 4 of those, okay? 4, so that would be 4 times 90.3 plus water in a gas state, and there are 6 of those. So we find water, H2O in a gas state, that's negative 242, and there are 6 of those. So all right, so we found our values on the chart. Now we need to remember our equation. Enthalpy is equal to the sum of the products minus the sum, the enthalpy, whoops, that's a terrible H, formation of the reactants. Remember, this is the one where they switch sides. Okay, so our products over here, that's 4 times 90.3 plus 6 times negative 242 minus 4 times negative 45.9, and oxygen is 0, so that's it on that side. So we do our math, come up over here with negative 1090.8 minus a negative 183.6. Do our adding here, we come up with negative 907.4 kilojoules. That's change in enthalpy. Okay? Again, using the chart. Don't forget your sig figs when you do this. Okay, in problem number 8, if the standard absolute entropy of O2, that should be O2, like this, gas is 205.0 kilojoules per mole, and the change in enthalpy is negative 114 joules per mole. What is the change in enthalpy of the reaction in problem number 7? So in this situation, we need to find, come on now, change in entropy, that just means standard temperature and pressure, remember, is equal to the sum change in entropys for the product minus the sum change in entropys for the reactants. Okay. So they give us oxygen, okay? Normally it's 0, but they gave it to us. So we can actually write this out. We've got 4 ammonia, and when we go to our chart, whoops, okay, here's our entropies. We've got NH3. NH3 in the gas state is 193. Okay, so over here we have 4 of them. So that would be 4 times 193. Our oxygen, it told us, is 205. We have 5 of these at 205.0. Okay. And then we have NO gas. So we go back to chart. NO gas is 211. So we have 4 at 211 plus H2O, water in the gas form. Back to our chart. Water gas form is 189. We have 6 of those. Okay, now don't get confused with this. This is just a line for the equation up above here. All right, so these are our reactants. These are our products. We need to switch them and put our numbers down. So now we have 4 times 211 plus 6 at 189 minus 4, it's a terrible 4, at 193 plus 5, this is the oxygen they gave us, 205.0. All right, so now we're just doing basic math here. We come out with 1978 over here. And 1797 over here. That gives us 181 joules per Kelvin, and that is our change in entropy. Okay, same formula that we used before. Just remember, it switches the product and the reactant for this, and we use the table. You will use this table for virtually every one of the problems that we have in this module, except for when we have the enthalpy equation in the Gibbs free energy equation. That's the only one that we won't use these tables for, but everything else will come from these tables. Okay? All right, last problem. If the enthalpy of a certain reaction, I know how to spell, is negative 623 kilojoules per mole, and the change in entropy is negative 114 joules per mole per Kelvin, what is the temperature range for which this reaction is spontaneous? Okay, so this is dealing with a question similar to what we did before. We've got our values. Let's write those down first. They give us the enthalpy change, which is negative 623 kilojoules per mole. Oh, goodness, this is going to take some time. Sorry. Okay. Our entropy is negative 114 joules per mole Kelvin. Okay, remember, this is in joules. We need to convert it into kilojoules, which is basically moving this decimal 3 spaces to the left. So that is negative 0.114 kilojoules per mole Kelvin. Okay, what is the temperature range for which this reaction is spontaneous? So this is the Gibbs free energy, and we want to find out when it's spontaneous. So we need to figure out what the temperature would be. So here's our equation. Gibbs free energy is equal to enthalpy minus temperature times entropy. Okay? We need to set Gibbs free energy to 0, remember, in order to figure this out. So that's 0. For it to be spontaneous, Gibbs has to be less than 0. Okay, so now we can isolate for temperature just like we did before. We'll bring all of this over to the other side. That gives us a positive T delta S less than delta H. And then we divide both sides by the delta S, so we get T is less than enthalpy divided by entropy. Okay, so we plug in our values now. So T is less than, our enthalpy they gave us is negative 623. And our entropy is negative 0.114. Okay, do our math. That gives us that as our answer. but we got to take significant figures into account. We have 3, so that takes us to the 6. So temperature has to be less than 5460. Or if we write it scientifically, it would be 5.60 times 10 to the 3rd power Kelvin. Okay, so for this to be spontaneous, the temperature has to be less than 5,460 Kelvin. There's your answer. All right, so that's it for this module. There's a lot going on here. Take your time. Remember, a lot of it comes from the chart, except for this equation right here. Okay, email me if you have a problem, and we'll see if we can straighten it out for you. Schoology was down all day today. Today's the 1st. Hopefully they've got it fixed and up and running. Good luck. I'll talk to you later.